So what an honor to be the last speaker. My parents has the wisdom to name me with the combination of X and the Z in my first and last name, so that I'm always listed the last. So I'm still the last one listed in the mechanical engineering faculty directory here. So that's a very easy way to find me. And it's very hard to pronounce as well, my name. So I want to talk about today is a little bit about my group's specialty on flame synthesis of metal oxide, and then how that leads you to look at today's topic is basically we're using water, oxygen from air, and when we shine light, and we're generating hydrogen peroxide, and this is spontaneous. It produces a little bit of electricity. So when we look at renewable energy, we want to think about how to convert renewable energy either to fuel or electricity. As an engineer, we think about devices. There are a number of devices to do that, like a fuel cell or solar cells. And if we look into all those devices, they have many things in common. One common thing is they all contain metal oxides. So when we think about energy problem in scale, that means we have to produce metal oxide in a scalable fashion at low cost. And many of those applications require exquisite design of the nanostructures of metal oxide. So the challenge is how to produce those metal oxide nanostructure at a scalable fashion. And my tool, it goes to my route on combustion, is to use flame as a reactor to synthesize them. Flame is very cheap and scalable, has high temperature, and it operates at ambient pressure. You may not know, actually, all of you own products from flame synthesis. Like the tire, carbon black, is made by flame synthesis. So anything like a rubberish, and that contains flame-made material. And actually, flame-made material annual production is almost $20 billion. So that's a huge market that shows the scalability. And over the past decade, my group has tried to synthesize different nanostructure of metal oxide. We started making metal oxide nanowires. And recently, we were able to control it down to a monolayer, sub-nanometer metal oxide material. And we also have techniques to dope those metal oxide to change their electrical and chemical properties. So how those materials perform in applications, one of the applications, as many of you have looked at, is on solar water splitting. I like it because it has the photo light absorption property, transport property, and also surface charge transfer property. And many of our flame processed materials shows better performance than other techniques. We also use flame to try to replace the traditional furnace. In this case, we look at dye-sensitized solar cell or perovskite solar cells. They all involve a process to use furnace to bake the TL2 paste. And normally it's about 30 minutes, and we replace it by high-temperature flame. Now we can do it in less than 1 minute. And our efficiency actually is a little better. Our flame-made material, because it's high temperature, is high quality, they can also serve as a very efficient hole doping material for many of the semiconductor devices. So that led us to look at a lot of solar water splitting using our flame-made oxide or doped material. We even developed flexible electrode for this case. We also look at the other side, the hydrogen side. We'll start to look at the molybdenum disulfide. We activated the basal plane for hydrogen evolution reaction by generating sulfur vacancy. So this is exciting. But when we look at water splitting, as many of you have said, this is really challenging. The efficiency is still not far from satisfactory. If we look at a little bit, there are side reactions going on here. If we look at the oxygen side, the water actually can be oxidized to hydrogen peroxide. And they look at the hydrogen side. If there's oxygen there, we can reduce oxygen to hydrogen peroxide. And hydrogen peroxide is a very important chemical. It's a strong oxidizer. If both sides can generate hydrogen peroxide, it's a liquid phase that may solve some of the problem with water splitting. And if we do this, do the electrochemistry, it's not a spontaneous reaction. It means we require some kind of bias. So I mentioned this is a side reaction. we have to compete with the regular water splitting. So we work with the Young-Snoskov group, and they did a lot of calculation. We did experiment. So the bottom line is we do find conditions and the material that prefer to form hydrogen peroxide. And now we can use that knowledge to build a reactor. And it looks like a fuel cell runs in a bucket of water. And with sunlight, as I mentioned, this is now spontaneous. But if we choose the right material, we can use photocarriers to make both reactions happen spontaneously. In this case, we're using BiVO4, and now the whole thing becomes spontaneous. To show you this is really happening, so I have some plot. The first one shows a chopping curve to produce hydrogen peroxide without any bias. It shows it produces hydrogen peroxide. On the other side is typical fuel cell measurement. It means while we are producing hydrogen peroxide, we produce a little bit of electricity, not a lot. The bottom shows we have the fuel cell in the beaker, and we have LED light. When we don't run the light on the fuel cell, it's dimmer, but when we turn the light on, our hydrogen peroxide fuel cell is generating additional electricity, make the light brighter. If the goal is to produce hydrogen peroxide, we can also apply a bias. So if we apply 0.5 bias, we can actually accumulate hydrogen peroxide to thousands of ppm level. And the really exciting thing is this also works on tap water. So if you just put tap water, put 1.5 volt, and it can also generate hundreds of ppm level. For water disinfection, we only need tens of ppm level. So it's not a very high requirement. So what's the future? And this is one of the vision we have with this spontaneous hydrogen peroxide generation system. We call it a solar-powered water disinfection. So we can use water, dirty water with bacteria, heavy metal, run through this fuel cell, light-driven fuel cell, and we can kill the bacteria, and only needs light. Another possibility is hydrogen peroxide is a strong oxidizer. It's on the, you probably have the 3% at home for disinfection. And it's a clean oxidizer. It can be used for many additional chemical production. So we can envision here using hydrogen peroxide as an intermediate for other oxidation reactions and use solar to power those reactions. So that's really exciting for the possibility. So with that, I want to conclude with light and water, a little bit air. Hopefully we can produce hydrogen peroxide. And thank you all for your attention.